Welcome everyone. In this lesson, we're going to be talking about more antiderivatives and indefinite integration, but this time we're going to see how to find the particular antiderivative of a function given some sort of initial condition. So the key word here, or key phrase here, is initial condition. And so when we first started talking about antiderivatives and indefinite integrals in the last lesson, what we kind of mentioned and what we were including every single time we found an antiderivative was that arbitrary constant plus c. We always included that at the end. And kind of the reason or the explanation that we're kind of thinking here is that if we start with the derivative of a function, what we're trying to do is we're trying to work backwards. We're trying to kind of recover the original function. And so we mentioned that with derivatives kind of destroy a little bit of information each time we do a derivative. And so we can do a pretty good job of recovering that original function with our integration techniques, but we can't recover the whole function. There's always this business of plus c at the end, so we're never quite sure up to a constant. But if we have a little bit of extra information about our function, which we'll call this an initial condition. If we have this initial condition, this extra information, then we can recover that specific antiderivative. We can recover our original function. All right, so this is going to be the main idea here. And then we'll see how this relates to actually position, velocity, and acceleration. So motion in a straight line. So we'll also see, given the position, velocity, or acceleration function, how we can then go on and calculate, depending on what we want, the position, velocity, or acceleration function, and we can go back and forth as much as we need, differentiation or integration. So let's start with an example. So example 1 here. We're going to find the particular antiderivative, we'll call this little f, of the derivative f prime of x equal to x plus 1 over square root x. So we're given the derivative, and what we want to do is we want to recover the original function. So we want to work backwards here using integration. And normally if we were just given this derivative, our answer would have plus c at the end. But this time we actually have, right here, a little bit more information about our original function. So this is our initial condition. That's our initial condition right there. And what this is saying is that our original function, when we plug 1 into it, we get 5. So this is all we're going to need to figure out what that plus c value is. All right, so let's get started. So first of all, how do we find the particular antiderivative? Well, we need to start by integrating this thing. So that's the first step, is integrate to get our antiderivative. We want the antiderivative. So basically, if we integrate the derivative, integration and derivative cancel out basically, and we get back our original function, and then we're going to have to figure out what c is. So this will include plus c. So let's start with and we'll keep the plus c on the other side. So we'll just say f of x. This is going to be our function. And then the plus c will be over here once we actually get the antiderivative. So we want our original function. So we're going to integrate it. We're going to integrate our derivative. So let's fill that in. So our function here is x plus 1 over square root x dx. We want to find the antiderivative of this, x plus 1 over square root x. And as it's written, there's a fraction here, and there's x terms on both the top and the bottom. So we don't really have an integration technique yet, or integration rule for how to handle these types of integrals. So our main strategy is, well, try to do the division first. So see if we can simplify this. And we can actually do the division here. So we can write this as x over square root x plus 1 over square root x. We can split up the fraction. So each term in the numerator kind of becomes its own fraction. So we get x over square root x, 1 over square root x, and then we have addition there, so we're adding those two fractions. Now once we have it, we can simplify each of these. So we can write x divided by square root x. If we want to write these in terms of power functions, we would get x raised to the 1/2 power. And then over here, we can rewrite this using negative exponents. So we would get x raised to the negative 1/2 power. Kind of our standard method for dealing with fractions and root signs. So normally we rewrite root functions. Kind of two things going on here. Square root x we would normally write as x to the 1/2. Just so that we have a power function, so we can use power rule. And then we also use negative exponents. So it's kind of our two standard techniques here. And the other thing to note here that might be kind of non-trivial, you might not think to do it right away, is just to actually do the division first. And the reason why doing the division first works is because we ultimately end up then with two power functions, and we can integrate each of those power functions. All right, so now we're at a point where we can actually find the antiderivative here. So we can do the antiderivative of x to the 1/2. So our variable is x. Add 1 to the exponent takes us up to 3/2. Take this new exponent, flip it, put it in front, so 2/3 goes right in front. That's the power rule. We're done integrating this x to the 1/2, so now we go on and do our second term. So here's our second term. We're going to integrate that one. And again, just power rule. So our variable is x, so we write x. Add 1 to the exponent, so it is negative 1/2 right now, but if we add 1, that takes us up to positive 1/2. Take this new exponent, flip it, put it in front, so it'll be 2 over 1, or just a 2. And then we originally had a plus sign there, so we're going to have a plus sign right here. And there we go. There's our antiderivative, but always remember the plus c at the end. All right, so there's our antiderivative. We found our function almost. So we almost have the function we're interested in. The only thing now is we got to figure out what plus c is. And that's the second step. We're going to find plus c, and that's where this initial condition, we're going to use it. All right, so let's write down our initial condition. We know f of 1 is equal to 5. That's what our initial condition says. Well, we also know what our function is. So we know f of x is equal to this whole thing. So let's actually plug 1 into what we have so far. So we're going to plug 1 right into what we have for our function so far. And that's what we're going to do. We're going to evaluate what we have. So we're interested in, what's happening to our function at x equals 1. So that's why we're plugging 1 in. Now we go up to what we have for our function. Let's plug x equals 1 in. So we're going to get 2/3, 1 raised to the 3/2 power, plus 2, 1 raised to the 1/2 power plus c. And if we clean this up, what do we get? We get 2/3 plus 2 plus c. And if we get a common denominator, well, you know what? That's fine. So we get a result here when we plug 1 in. And so what we want to do, we want to find the c value that makes this value right here match up with what it needs to be. It needs to be 5. So we want these two values to be the same. So what we're going to do is we're going to set these two values equal to each other and then solve for c. So we're going to set these two values equal to each other. And when we do that, we're going to get the equation 2/3 plus 2 plus c is equal to 5. And now we just solve this for c. All right, so subtract 2 from both sides, subtract 2/3 from both sides, and when we do that, we get c is equal to 7/3. And it always feels like when you get c is equal to the number, it feels like that's the answer. It's not quite the answer. So what we're trying to do is we're trying to find the particular antiderivative little f. So what we did in step 1 is we found the function, except we didn't know what c is. In step 2, we actually found what c is, and so the last step is to just put it all together and actually answer the question. So last step is put it all together. And so we take what we found for little f of x. We said it was 2/3 x raised to the 3/2 power plus 2 x raised to the 1/2 power. And then we had c, but now we actually know what c is. It's 7/3. So plus 7/3. And there we go. We have our particular antiderivative. So not only is this function an antiderivative of this f prime, but it also satisfies this initial condition. So to recover the function exactly, the first step here is the integration. That gets most of it. And then the second step, we use our initial condition to actually figure out c, and then we just kind of put all the pieces together, and we have our particular antiderivative. All right, and that's generally the process. So we'll try a few more examples like this, and then we'll see how we can use these ideas to help us with objects moving in a straight line with position, velocity, and acceleration. But let's try another example. We'll see you there.